Hi, my name is Stuart Ozer, and this is Lab 4 for Physics 2211K. The purpose of this lab is to understand and predict the motion of a spring and weight oscillating on a swinging spring. So the models and fundamental principles here are Newton's second law, F equals ma, energy principle, E equals K plus potential energy in the system, gravitational potential energy, which is mass times gravity times height, change in height, spring potential energy, which is 1/2 s squared, the position update formula, Pf equals Pi plus velocity times delta t. The velocity update, Vf equals Vi plus acceleration times delta t. Kinetic energy, which is 1/2 mass times velocity squared. The oscillation period, which is 2 times pi times square root of m over k. The system here is the mass, spring, and the earth, and the surroundings is, of course, nothing. So this is a brief preview of the results we'll get to in a minute more, but as you can see, the model predicted actually very well as the delta E was completely unchanging. And we'll get to these offsets in a little bit. So the experiment, the initial conditions for the experiment was the mass was 0.402 kilograms, the gravity was 9.8 meters per second squared, spring constant K was 6.83 newtons per meter, and L0 was 0.123 meters. And this is the tracker data over here. As you can see, that very nice periodic motion in the x direction, and in the y direction it goes down, and I'll talk about that in just a minute. So here's what the video looks like, just a short clip of it. So that was the motion of what the spring and mass was doing. And so here's the code here. We just established our initial conditions here, and then here, here, and here. And then we said that L there, and the length of the spring is the ball dot position minus the spring dot position. And then we found the hat vector there with L over the magnitude of L, and then S is mag of L minus L0. And then using the equations we talked about earlier for kinetic energy, potential energy, and spring potential energy, the first one is gravity potential energy, we find those things, and then we sum up the total energy to be K plus the potential energy in the system. And then in the while loop, we redefine those to be, we define the initial energies to be those values, and then the force of gravity is negative mg, force of the spring is negative 1ks times L hat, and then F net is force of gravity plus the force of the spring. And then we apply the update formulas. We recalculate the length of the spring, and then we recalculate the energy changes down here with those same formulas, and then the change in energy is just the new energy minus the initial energy. And so those produce these graphs where you can see that the orange line here on the change of energy is always 0, and it's perfectly horizontal, which means the model predicted a perfectly constant total energy, which is exactly what we wanted. But this is actually a perfectly constant total energy in the system that we considered in the model is actually not what is really happening in the real world, because in the real world it's not an isolated experiment, which means we don't calculate for air resistance in the model, which will slowly slow down the y position versus time and slightly the x position versus time, but the y is much more drastic. As you can tell, it's literally 6 times more drastic. And the reason this y is all negative is because it all happened below the origin. And the tracker data is kind of jagged, and that's because the tracker time steps are significantly more than the model time steps. And then the initial conditions for the position may slightly be off, which is why you have this gap here. But otherwise, the period of oscillation is modeled very well for both the x and the y. And I discussed that the y is most likely due to the fact that we didn't calculate for things such as air resistance that slowed it down in the y position, that we just didn't account for in the x position. In the model. And other human estimates are also possible sources of error. So for the what does it mean questions, for the first one, yes, the total energy remains horizontal at all times, a constant value, so the energy principle is satisfied. And the code actually has this graph, the orange line, plotted by summing the values in the graphs of kinetic and potential energy, which means that K plus potential energy in system always equals a constant total energy, which is exactly what we wanted. And then for question 2 about the oscillation periods, we got that the oscillation period for X was around 1.614 seconds, and the oscillation period for Y was around 1.519 seconds. And these are very similar, but they are different. They were calculated by determining the time of one full oscillation using that tracker data. And then the slight difference holds true to the experiment, as they both looked basically the same, but you could tell it was slightly off because they got worse and worse as the video went on. And so that is the end of the lab. Thank you.